Thanks. Okay, so yes, I'm going to discuss a little bit the status of these algorithms for primary vertex and track clustering in CMS and how we are dealing to put this into a GPU, which it's been a relatively lengthy task. So first of all, let me contextualize this a little bit by discussing how why we need to do this from the CMS point of view. So of course, I think it comes to no surprise to everybody in the talk, but the point is that as we go further in time in the LHC, there are going to be several changes corresponding to the run 3 and then the high luminosity LHC, in which we expect significant more challenging conditions in which the instantaneous luminosity increases. So we're taking more data taken per each second. So in the sense, we need to modify or work in algorithms to be able to deal with this. And this, in fact, is strongly related to the modifications to the HLT, the triggering code that we're already covering in Adriano's talk yesterday. And then on top of that, we are also collecting more data. We are going to collect more data. The integrated luminosity is also going to increase. So we not only need to take care of having a performant triggering algorithms, but also start taking a look at the kind of reconstruction algorithms that we run offline after the data has been taken. And this is a computational challenge because with the current budget, and I'm showing here some extrapolations that were done last year, and with the current resources we have, if we don't do anything, we are going to basically run out of computational resources to process all of this data we are taking. Even if we're able to do it at the triggering level, whenever we want to run an algorithm, a reconstruction algorithm offline, this is taking a significant part of the CMS computing power, as it is shown in the plot in the bottom right. So one of the challenges right now for the experiment is to try and find, do R&D and try to find different ways of processing data so we can tackle this problem. And one of the things is that, as we know, that the online algorithms are already been successfully offloaded to GPU-based architectures. This shows for us an open path to do the same with the offline reconstruction, which has been going a little bit behind it. And amongst them, what I'm going to discuss mostly is the picture of how this is done for vertexing, which is, if you look at the picture on the right, is kind of a summary of how the reconstruction time is employed in the CMS experiment, and roughly around a 10% of it is what is spent on this vertex, on finding the primary vertex in the collisions. Roughly it can be divided in 3 steps, what we do, which are a first filtering step that is known as track selection, which is just taking the inputs we'll discuss a little bit more later, and then just selecting the things that make sense to the clustering. Then a clustering step, which is just grouping tracks that are close by into what are sets or vertex candidates that represent our primitive vertex candidates, and then fitting, which is obtaining properties of these vertex themselves. And if you look at the time splitting plot that is here in the bottom left, what happens is that we go towards harsher conditions, so towards higher average pileup interactions, which is towards this run 3 and mostly towards these phase 2 conditions of the LHC. This clustering steps is taking most of our time, and so this is the one we want to tackle. To do so, first of all, just to introduce everybody, so how we do this. So the idea is that we have all of the tracks that we are reconstructing at the CMS detector, and then we filter a small set of them that we consider interesting or have an quality to be considered for the vertexing. This is basically based on the properties in terms of the number of hits we register on the detector, the consistency with having originated at the beam spot, and several other properties. The idea is that we reduce the whole problem of dealing with the whole tracks to just having them into a single coordinate, which is the set coordinate, the coordinate along the axis. And so we reduce each of the tracks to a single position, which is represented by these dots. and an uncertainty, of course, in how well we are measuring this position. And then what we have to do is play with this to try and find, which here seems a little bit evident in this picture, but the idea is to try and find some clusters or some groups of them that could be consistently coming from the same primary interaction, coming from the same primary vertex. And the underlying idea we want to reach is to get something that is close to hard clustering, so having each track univocally associated to a vertex. And again, the idea is that we have all of these tracks, which are as these dots, and we want to put them into these boxes, which are these groups of vertexes. And so at the end, you can formulate this as a optimization problem, which we are trying to find the overall number of vertex that appear in an event, their positions, which are this set case, and also the assignment of each track to its vertex. So a variable that is 0 if a track and a cluster are associated, or 1 if not. This by itself, it seems like a simple optimization problem, but in practice introduces a lot of issues. Mostly, well, the principle of them is that the overall number of vertices is not fixed. So the number of vertex candidates needs to be extracted from our data as well. And that as we are going into harsher and harsher conditions, we expect so many vertexes that most usual or optimization techniques are likely to fall within a local solution or a local minima instead of a global one. So what we are playing around with is with an algorithm known as deterministic annealing. And the idea is that instead of going with hard clustering, we are fuzzing the assignment. And instead of doing a one-to-one assignment between tracks and vertexes, we are assigning to each track a probability different from 0 or 1 in assignment to its vertex. And to fuzzy this assignment on top of what was previously discussed function that corresponded to hard assignment, we have a penalization term that represents kind of an entropy and a mixing between the different, that introduces kind of an entropy term of all the probability assignments. So instead of having hard clusters, we have something that if you go to high temperature are kind of fuzzing together, so they kind of overlap between themselves. And as you go to lower temperature, the thing starts being more resolved. You get something that has much more hard cluster, hard vertexes that are well isolated. And the idea is that this algorithm can improve the several problems I pointed out before, because you can deal with them in a similar way, so in a kind of constructive way. And the thing is that instead of fully optimizing this formula for each t, you can start with an analytical solution that is unique at a high temperature, which is having a single cluster that aggruppates or groups all of the tracks together. And this is, of course, a solution of minimal entropy. And the idea is that you can go from this solution by varying parametrically the temperature towards a lower temperature, so towards the region of hard clustering. And you can do so smoothly in such a way that you are going towards analytical solutions of analytical minima of these equations by doing a smooth transition. So you can reach from the maximum entropy solution to the completely hard clustered solution using an analytical transition going through the parameter t. The idea is that once t is small enough, you reach a point in which this hard cluster is split into two, and then you can basically compute minima of this equation that lets you compute solutions for the probability of assignment and the positions of the vertex depending on the temperature. So if you do this iteratively with small steps in t, you can again reach an evolution of the solution that goes as the temperature decreases, goes towards the region in which you reach hard clustering. And the idea, or what has been proven for this, is that this converts to the global solution with much more efficiency than the origin, than a directly hard cluster tends to do. And also, as well as you have these splittings, depending on the temperature parameter, has an analytical way of also defining the overall number of vertex you are expecting in each event. The problem, of course, is this is extremely complex, and as an algorithm, And once you try to put this into a GPU implementation, so something that tries to profit from the fact that we have a lot of inputs, you have to run a little bit the numbers. And in fact, a priori this seems good, because if we go from the run 2 and we have around 20 vertex, around 500 tracks, we are looking at around 10,000 or so assignments between tracks and vertex that you have to keep track. And this is for the current running conditions. If you go to the future, what we want to work towards, we are talking about 2 orders of magnitude more of events. And so this, in principle, seems like in a case in which you have to keep track and compute simultaneously so many numbers, is kind of a place where you think it's going to be very nice to do parallelization, to work with GPUs which are able to do this in an optimized way in parallel. And so the challenges at the end is to put this into a GPU that is able to keep track of these 10 to the 6 parameters, and then to organize it efficiently so in such a way that you don't lose significant performance in terms of time. And so this is also slightly related to...
Carlos, you have 4 minutes.
Thanks. And this is slightly related to the topics that Adriano discussed in yesterday's talk, which is at the end what is complex for us is to try and store things or work with things in a proper format, which is this scalar of array formats in which we are literally saving all of this into a single object. So instead of having properties of the tracks and properties of the vertex separately, we are trying to save all of these probability assignments completely into the data format as we're using for representing the tracks in the code. This is, unfortunately, this also presents some challenges in GPU implementation because this is a lot of information. So, and in fact, that we don't know the input number of the number of vertices we are going to end up. So we really cannot define a priori how much space we need to store it. And the way we're dealing with this is we are just getting an oversized space in the GPU memory. We reserve it and zero pair it, so we are able to then put all of the outputs of the algorithm as the vertex collections grows and grows as the algorithm evolves. The other challenge that we face is trying to put this into a multi-threaded way that is optimal, and to do so we have to massage a little bit the equations, and we are able to reach things that look like this, that are a bit more complex like this, but the idea is that we can basically put all of the equations of the evolution of these assignment probabilities and positions into a way that is able to run in parallel across all of the numbers, and so we can make profit of all the multi-threading capabilities of a GPU. So we can run this in parallel across all threads that go into a single block inside the GPU. The only problem we reach here is that, of course, as we need to synchronize all of the threads after we do an updating step of these quantities, we are somehow limited nonetheless by the number of threads in the GPU. So we cannot, of course, parallelize to 10 to the 6 quantities at the same time. That said, so we have managed to put this into a GPU, and in fact, we have already a first implementation of this deterministic annealing running both into a CPU and a GPU. And we have been able to prove that a GPU implementation is not only possible, but also has a comparable timing in terms of how much time is spent per event by comparing this inside a CPU, which is an Intel GPU, a very normal Intel CPU, and a Tesla T4 GPU, which is also one of the standards that is currently being used for CMS for the HL-LHC. And in fact, we have also been able to prove that these fully synchronized results, meaning that we obtain the same results between the CPU and the GPU for this deterministic annealing algorithm. There are still some things that can be considered for the future, like running this in parallel for a small subset of the detector, which we consider might be one of the possible ways of making this even faster. But in fact, what we want to stress is that we are already having some notable results porting this as a first step into a GPU. And I'm running out of time, so let me go to the summary. So we try to discuss a little bit the kind of algorithms that we are currently running for offline primary vertexing in CMS and how we are trying to put this into a GPU. And in fact, this is one of the first steps we need to try and reduce the overall computational needs of the experiment. Of course, this will improve if other parts of the reconstruction are also put into GPU, so we can profit from running the whole thing, the whole chains without depending on CPUs. But in fact, this shows already some promising results that are for sure going to be part of the CMS strategy going forward. And I think I ran out of time, so I'm going to finish things here. And yes, thanks everybody for listening.
You were perfectly on time, Carlos. Thanks. Questions from the room. Let's start with the room this time. Okay. Questions from Zoom. Right. So, Carlos, I have a question. Have you looked into other clustering algorithms other than deterministic annealing?
Yes, this is something we are considering in parallel as well. Going from things that are currently used also for other parts of CMS. So we have tried the different algorithms that are already running in HLT. We have also considered things that are a bit more classical, like k-means, things like this. It's kind of a work in progress to see if we can even improve the performance in that way. But we are checking them.
Anything else? All right. Everything very clear, actually very interesting. Thanks again, Carlos.